Good afternoon, dear Chairman, dear participants. Let me introduce myself to you. I am Dmitry Kosov. I am postgraduate student of Kazan Scientific Center of Russian Academy of Sciences. The title of my talk is Complex Stress State Analysis for Aluminum Alloy Accounting for Damage Accumulation. The work was carried out jointly with Dmitry Fedorenkov and Andrei Tumanov. My report will consist of 4 parts: motivation, implementation of the Lemaitre model, experimental study, and numerical study. Some words about of motivation of our study. The behavioral structure of material under a complex stress state has been the subject of theoretical, experimental, and numerical study for many years. Structural elements of aviation equipment, power engineering pipelines are exposed in operation to the action of a complex set of mechanical and thermal effects causing a complex stress state. In structural elements such as aircraft landing gears, there are internal and external stress concentrators in the form of a notch of various profiles. During the loading on the material, micropores of the crack are formed inside it, which lead to the destruction of structural elements. In order to accurately predict such mechanism at the product design stage, damage model must be used. The use of such model in the finite element method can be a useful tool for design and operation of structural elements. In this study, we use the Lemaitre damage model. To implement static loading, it's necessary to use the isotropic hardening law to describe the deformation process, as well as the damage accumulation law to describe the damage accumulation process. Damage accumulation process depends on the damage strain energy release rate. For application to the case of multiaxial loading, a multiaxial function is introduced. In this study, a comparative analysis of the exponential law of isotropic hardening and the power law. The Lemaitre damage model was integrated into the ANSYS software package as a dynamic link library to determine the effect of damage on the stress-strain state of a material under a complex stress state. Next slide shows the algorithm for determining the stress-strain state taking into account damage. The strains obtained using the finite element method are multiplied by the elastic model and the elastic stress is determined. That is, the first stage is reduced to solving an elastic objective using the classical Hooke's law. At the second stage, it's necessary to jointly solve the law of isotropic hardening and the law of damage accumulation. As a result of solving the system of nonlinear equation, we determine the stress, the value of plastic deformation, and the value of the damage parameter. The difference between the red and blue curve describes the process of damage accumulation. The next part of my report on experimental study. Experimental data are needed to determine the parameter included in the Lemaitre model. At the first stage of the experimental study, a Uniaxial tensile test of a cylindrical specimen was carried out to determine the basic mechanical properties of the aluminum alloy 2024. The result of the test is a Uniaxial tension diagram as well as the main mechanical properties of the material presented in the table. The resulting diagram was approximated by exponential and power laws. The diagram shows the difference between the tension diagram and approximating function in the initial section of elastic plastic deformation. It was found that for the aluminum alloy 2024, it's preferable to use the exponential law of isotropic hardening, since when using the power law there is large deviation from the experimental curve. The object of the second stage of the experimental study was a whole cylindrical specimen with a notch. The thickness of the cylinder wall in a smooth specimen and in the minimum section of the specimen with notch was 1 mm. The program of experiments included various combinations of axial force, torque, and internal pressure applied to a cylindrical specimen. The values of limit loads and torque moments obtained as a result of tests are given in the table. The next part of my report on numerical study. At this stage, we have carried out the implementation of the Lemaitre model using the obtained experimental data such as material properties and limit loads. First subject for numerical study is smooth cylindrical specimen. To verify the parameter of the damage accumulation model, a Uniaxial tensile test of the aluminum alloy 2024 was simulated. To reproduce the experiment, points were set on the model with a point of contact between the extensometer and the specimen. The boundary conditions were modeled by applying displacement to the gripping part of the specimen up to the value of which the specimen was filched on the experiment. The result is a uniaxial tension diagram shown on the slide. The slide shows the result of two numerical calculations, using the law of damage accumulation and reach-out. The difference between the diagrams obtained characterizes the accumulation of damage. It can be concluded that when analyzing the stress-strain state, it is necessary to use the law of damage accumulation. Next subject numerical study is whole cylindrical specimen with notch. To analyze the stress-strain state of the aluminum alloy 2024 under a complex stress state, three-dimensional design schemes were formed from 20-knot volume isoparametric element. In the zone of the notch, the mesh was thickened to determine the stress distribution and the damage parameter over the thickness of the specimen. A matrix of calculation of a whole cylindrical specimen with an annular undercut under the influence of various combinations of laws presented in the loading diagram has been produced. The result of the numerical study, namely the value of the damage parameter at fracture, are presented in the table. Next slide shows the distribution of accumulated damage along specimen thickness for different complex stress states. For a quantitative analysis of the damage distribution, the damage parameter was normalized to the maximum damage value from the entire calculation matrix, which is 5.41%. The maximum value of the damage parameter is achieved with a combination tension plus torque plus internal pressure. This type of multiaxial loading is the most dangerous. In Figure B, a qualitative analysis of the distribution of the damage parameter over the wall thickness in the zone of the annular undercut was carried out. It can be seen from the graph that under loading, tension plus internal pressure plus torsion, the accumulated damage is distributed over the entire thickness of the wall, and the maximum value of the damage parameter is absorbed off the top of the annular undercut. However, under loading, compression plus internal pressure plus torsion, damage accumulation doesn't start from the inner wall, but from the middle of the wall section. Next slide shows the distribution by axiality ratio over the wall thickness. The analysis of stress distribution effect in the specimen of the considered geometry was carried out on the basis of the stress biaxiality ratio. The biaxiality ratio determines the ratio of axial stresses to tangential stresses. On figure, it can be seen that in all considered cases of loading, the biaxiality ratio at the top of the annular undercut is in the range 1.9 and 2. Behavior of stress biaxiality parameter is important for practical application. Next slide shows a limiting state diagram. The traditional way to assess the effect of a complex stress state on material properties is to compare experimental data with classical strength theories. For this purpose, the theory of maximum normal stresses, the theory of maximum shear stresses, the generalized Pisarenko-Lebedev criteria. The slide shows limiting stress values for 6 variants of a complex stress state and numerical determ, taking into account the damage function. Conclusions. The object of the study was smooth specimen and hollow specimen with a notch. The values of limit stresses were experimentally determined when testing whole cylindrical specimen for tension, torsion, internal pressure, and the combination. The possibility of using the Lemaitre model in a complex stress state taking into account damage is considered. As a result of numerical calculation, damage accumulation trends for each type of complex stress state were determined. The most dangerous stress strain state form in terms of damage is determined. The result confirms the preferences of using the Lemaitre model due to sensitive to damage accumulation and the type of multiaxial loading. Thank you for your attention.